So now we want to kind of take what we've been doing with series and bring it back to functions. So you might have noticed that we've pretty much taken a break talking about functions up to this point. We were talking about sequences and then we were talking about series. And we had a little bit of functions in there, like when we talked about the integral test, for example. But for the most part, we haven't really talked about functions, which is, what we've been talking about this whole class. So we want to bring this back to functions now. So the idea that we're kind of working up to, the whole reason that we're really looking at these series is because we're going to work up to the idea that we can take any function, well, not any function, but most functions, and represent them as an infinite series of polynomials. Okay. So if you think about what that means, that's a very powerful idea that we can basically represent any function. If we can represent any function, or most functions again, as an infinite series of polynomials, then that means that we can approximate functions as a finite series of polynomials. And that's really useful because polynomials are by far the easiest functions we have to work with, right? When you think about like the exponential function, logarithmic functions, the trigonometric functions, all the other types of special functions that we have, none of them are as easy to work with as polynomials are. Polynomials are continuous. They're defined on the domain of negative infinity to infinity, right? So they're easily the most well-behaved function. So that's a very powerful idea. So that's what we want to work up to. So this is kind of the first step to that, is bringing this idea of functions, or this idea of series back to functions. And that's with the idea of a power series. So we'll start with the definition of a power series here. Okay. So a series of the form n equals 0 to infinity of c sub n x to the n. So this will have the form c sub 0 plus c1 x to the 1 plus c2 x squared, etc. Right, where the cn's are just any coefficients, right? That's why we use c here. Sometimes you'll see an here, and that's fine too. It's not really important what letter we use. So a series of this form is a power series. And we say it's centered at 0. And we'll kind of get into like what that means as we look at the series more. So this is the general form of a power series centered at 0. And if we want to center it somewhere else, we can tweak the definition a little bit. Okay, so a series of the form, basically the same thing, but instead of x, we're going to have x minus a to the n. So this is going to look like still c sub 0 plus c1 x minus a plus c2 x minus a squared, etc. So this is a power series centered at x equals a. Okay. So some books will just kind of focus on the centered at 0 form of this because it doesn't really change a whole lot. We just move everything over basically if we want to center it at a different number. That's what this does, right? It would be like a horizontal transformation, moving everything to the right a. So the math isn't changed too much here. So because of that, some books will just focus on this form because it's nicer. It's a little simpler, but ultimately it's not going to change too much. Now, one thing that's a little weird here, and this isn't super consequential to anything, but In this context, x to the 0 is usually defined as 1, even when x equals 0. Okay, so normally 0 to the 0 is indeterminate, but there are specific cases where we might define it to be something different. Like here we define it to be 1. And we don't really have any trouble doing that. The only reason you wouldn't want to do this, why we don't give other definitions to these indeterminate forms or these undefined forms, is because they lead to contradictions. Like, for example, if you just, you'll see like these weird like tricks on certain videos that'll go viral every once in a while, where somebody will show that like 1 is equal to 2 or something like that. And almost always there's somewhere in there they're sneakily dividing by 0, right? So that's why we don't allow division by zeros, because it can lead to weird contradictions like that. But in this context, this doesn't lead to any weird contradictions, so we're able to comfortably do this. Okay. So again, it's not super consequential here. It's just something that is done for convenience. So we don't have to specify that x isn't 0 every single time or something like that. So just some examples here of some general power series. So for example, n equals 0 to infinity of x to the n over n factorial. This is a power series. So note the difference here is that we have now a variable in here, right? So x is now, we're introducing a variable. We didn't have any variables before. We had this n, but it's not really a variable in the traditional sense, which is that it wasn't like, we weren't defining any kind of function or anything like that, right? This was, it's the index, right? And at each step, we know exactly what n is. So x is now more of a traditional variable, and we can define this as a function. So like we could call this f of x, for example, because x is the only true variable here. N has a value at each step, right? So this is an example of a power series, a pretty important one that we'll see later on. So it would look like 1 plus x squared over 2 plus x cubed over 6, etc. Right? This is the first time where this factorial is going to start coming into play a lot, because this is in the formula for what we call a Taylor series, which is the version of what I was talking about at the beginning of this video, where we can represent a function as a polynomial. So definitely start getting more comfortable with the factorials if you're not already. Some other examples, we could even have the n factorial on the top. That's still a power series. Okay. One that's not centered at 0. We could have x minus 2 to the n over n plus 1 times 3 to the n. Okay, so a bit more complicated here. This is a power series centered at 2, right? So it would look like 1 plus x minus 2 over, this is going to end up being 6, plus x minus 2 squared. This will end up being 27, etc. Okay. So one thing that we'll be concerned about with the power series, of course, is whether or not the series converges. And it's not just going to be if it converges, it's going to be specifically for what x values does it converge. Okay. So we know, like without the x at this point, how to determine if the series converges. But now that we have this additional variable in here, which can take on different values, we want to know, okay, what values of x will allow this series to converge. So we want to bring all of the convergence stuff that we did into this context now. So it can be a little bit trickier because There's a lot of different values of x we have to consider. So it's helpful to be pretty familiar with these different types of infinite series. So let's just look at this theorem here, which concerns the convergence of a power series. Okay, so consider these series n equals 0 to infinity, c to the n, x minus a to the n, the centered at a version. Then the series satisfies one of the following, okay, and only one of the following. So it's either going to converge at x equals a and diverge for all x not equal to a. Okay, so this is kind of the extreme case. So any power series is trivially going to converge at x equals a because that's just a series of zeros, right? It would just be 0 plus 0 plus 0 plus 0. Technically, the first term would actually be 1, right? Because you would actually have 0 to the 0th. So it would actually be c sub 0, I guess I should say. But so it would be 1, or rather c sub 0 plus 0 plus 0 plus 0 plus 0, right? So it's going to converge in that case. So this is kind of the extreme where this is the only value it converges at. It could converge for all real numbers. All real numbers x. Okay, so maybe it doesn't matter what x is. Maybe it just converges no matter what. Okay. Or the more common case is that there's going to be a certain interval where it converges. So the other scenario would be that there exists a real number r greater than 0 such that the series converges if the absolute value of x minus a is less than r, okay, and diverges if the absolute value of x minus a is greater than r. So there's this cutoff point where if x minus a is lower than this number r, then it will converge, and anything past that it will diverge. Okay. Specifically when x minus a equals r, it could go either way. Okay. So in these scenarios, we'll need to actually test the endpoints here specifically to see if it converges or diverges. Okay. So let's look at some examples here. Actually, I meant to actually write here as well. R is called the radius of convergence. Okay. So it's called the radius of convergence. So it's kind of giving you the length of the interval where it converges. Okay. So in the extreme examples, in this one, r equals infinity if it converges for all real numbers. And if it converges for none, we would say that r equals 0. Or it only converges for one number, but we would still say the length of that interval where it converges is 0 because it's just a single number. Okay. So the interval where x converges naturally is called the interval of convergence. Okay. So typically for a power series, then we're going to try to find the interval of convergence, which will give us our radius of convergence if we want that. Okay. So let's go ahead and look at how we can find that then. So if we look at the one, the very first one that we mentioned, n equals 0 to infinity of x to the n over n factorial. We want to look for what values of x does this converge for. Okay, so we did see that 1 over n factorial converges, I believe, in a previous video. So we know that it converges for some values of x. We know that it converges for x equals 0, right? That's just always going to be true no matter what. So, but we need to know exactly what values it converges for. So we want to use our past convergence test. In this kind of scenario, the ratio test would work out the most nicely because basically whenever we have n factorials or something to the n power, that's really the only test that works out too well for us, right? Convergence test is going to be hard to use for these because, we're accounting for all values of x, right? So there's really only going to be specific scenarios where you could even use that. I would say most of the time we're going to end up using the ratio test with these ones. So this is going to be x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. And that's the limit. Okay. So we can't drop the absolute value. A lot of times with the last ones, we were just dropping the absolute value because we would establish right away that everything was positive or just get rid of the negatives, right? But here, x, we don't know what x is, so we can't just get rid of those absolute values, okay? So this is going to be, we'll rewrite some of the steps here, or some of these equations, x to the n over x, n plus 1 times n factorial, and then this will be times n factorial over x to the n. So same kind of process we were using before. So this is going to be the limit as n goes to infinity of x over n plus 1. Now we're only taking the limit as n goes to infinity. So x in this case doesn't affect that limit at all. So we can actually pull the x out. So anything that's not part of this variable is kind of treated like a constant, and we can bring it out in front of the limit. Okay, we have to keep the absolute value with it, but that's okay. I mean, at this point, we don't even need the absolute value over here, right? Because we know 1 over n plus 1 is positive. But we pull that x out because it's not dependent. The limit does not depend on that x because the limit is about n. So now this is going to be equal to 0, right? So this is going to be 0. So what this is telling us is that no matter what the value of x is, this limit is going to be 0, right? We can plug in any number we want for x here, and this limit's still going to be 0. By the ratio test, this is less than 1, so it converges. And because it doesn't matter what the value of x is, this converges for all x. Okay. So the interval of convergence we would say is negative infinity to infinity. So you might say like IOC, interval of convergence. Radius of convergence, or you might just call it R, is equal to infinity. Okay. All right, so let's look at the other ones that we had written down before. So the other one, the second one was n factorial x to the n. Okay, so we'll look at the limit as n goes to infinity of n plus 1 factorial x to the n plus 1 over n factorial x to the n. Okay, so we do our rewriting here, n plus 1 times n factorial x to the n times x. And then that'll make everything cancel here. Again, we can pull this x out. So I'll just do it on the same step here. So we have x, limit as n goes to infinity of just n plus 1. And now again, it doesn't matter what x is, this limit is always going to be infinity, right? So what x is doesn't matter unless it's 0. So then we kind of run into a weird situation with the ratio test. So that's why it was important for us to establish those ground rules in the first place, which is that this is going to converge at x equals 0 no matter what. Okay. But anyway, so this is greater than 1. So this means that it diverges for all values of x except for x equals 0. It's always going to converge for the value x equals 0. Okay. So we would say that r is equal to 0. So diverges for all x not equal to 0. Okay. So this would be our final answer here. You can't really write it as an interval. It's just one value. So you could just write x equals 0 for your interval of convergence if you want to. All right, and then finally, the last one we had written down there, the one that was not centered at 0. Sorry, I'm just trying to think of what it was here. X minus 2 to the n over n plus 1 times 3 to the n. There we go. So this is centered at 2. So we're going to do the ratio test like we did before. So we're going to get x minus 2 to the n plus 1 over n plus 1 plus 1, which is n plus 2, 3n plus 1 over x minus 2 to the n over n plus 1 times 3 to the n. Okay. So we'll go ahead here and rewrite this. So we'll get x minus 2 to the n times x minus 2 over n plus 2 times 3 to the n times 3 times n plus 1 times 3 to the n over x minus 2 to the n. I don't know why I wrote 2 up here. It should have been to the n. So cancel some stuff out here. Can't cancel the n plus 1. And n plus 2 here this time. But that's okay. So I'm going to pull out the stuff that the limit doesn't depend on. So the x minus 2 and the 3. Okay. So x minus 2 over 3. We don't need the absolute value around 3. We know 3 is positive. So this is n plus 1 over n plus 2. So this limit is going to be 1. So this is going to be equal to x minus 2 over 3. So this is going to converge via the ratio test whenever this is less than 1. Okay. So specifically, we would say this converges when x minus 2 over 3 is less than 1. Okay. So this is going to leave us with an absolute value inequality that we need to solve. So you'll want to kind of brush up on these. So this is x minus 2 is less than 3. So this means that negative 3 is less than x minus 2 is less than 3. If you want to write it all out as a compound inequality, that's probably the easiest way. And then you just add 2 to every side here. So you get that x is between negative 1 and 5. Okay. So we know that it converges. So let me say we know that it converges on negative 1 to 5. But we need to test the endpoints. Okay, so specifically because if x is equal to negative 1, if we look at the initial limit here, if x equals negative 1, this is going to be the absolute value of 3 over 3, which is 1, and that's going to make the ratio test inconclusive. Okay, so that test, so we're going to need to do a different test at that point specifically. Same thing with 5. If x is equal to 5, this is also going to be 1, so then the ratio test is inconclusive. So these can get a little bit lengthy in these situations here. So we'll test specifically x equals negative 1. Okay. So let me just scroll back up to the original series here. So x minus 2 to the n over n plus 1 times 3 to the n. So this would become negative 3 to the n over n plus, n plus 1 times 3 to the n. So this is equal to negative 1 to the n times 3 to the n, n plus 1 times 3 to the n. So we can cancel these out. And this should be the series here. So we're looking at this series right here. So to determine if this converges, this would be a standard alternating series test. And we can say, I won't go through the details here, but this does converge by, let's say, alternating series test, AST. So, namely, the limit is 0, and it is a decreasing sequence, the 1 over n plus 1 part. Okay. So we're good with negative 1. Now we need x equals 5. So, again, it was x minus 2. So it would be 3 to the n over n plus 1, 3 to the n. Okay. So we plug in 5 for x and we get 5 minus 2, which is where I get the 3. So these cancel. We get n equals 0 to infinity of 1 over n plus 1. And now this is basically the harmonic series, which we know to be divergent. Okay. So when it starts getting to common series like this, you don't necessarily need to show it every single time if that's not the focus. Like if you're in the context of finding this interval of convergence and this is a series you've seen a million times before and you know right off the bat that it's not convergent or it is convergent, then you can just say that and you can say what test you know this by. Like we could just say P series. And really you're doing like a P series or a comparison test, or maybe you're doing an integral test. I guess that would probably be the most direct way, is just to say integral test. But as long as it's kind of close and I don't think you're just making it up, then yeah, that's fine. So this series converges on negative 1 to 5. Okay. And we would still say that the radius of convergence is 3. The endpoints aren't going to affect the radius of convergence. And remember, the radius would be half the length of the interval. So this interval has length 6. So the radius would be 3.